Why do video games seem to be getting worse performance and graphics year after year? Even with the new flashy graphics cards, computers that look almost alien, and more money than ever being poured into the industry, don't you find it strange how newer games not only seem to run slower, but also look less graphically impressive than similar older games that ran flawlessly on weaker hardware? So today, we're gonna find out who's really to blame. Is it the developers, the game engine, or something else entirely?
It is evolving, just backwards.
But before we point any fingers, we have to look at where things first started to understand the blurry visuals, the laggy frame rates, the game-breaking bugs, and the angry Steam reviews. Back in the day, games were made for only one thing: consoles. Some of the most legendary games of all time came out of this era. Shadow of the Colossus pushed the PlayStation 2 to its limit with huge landscapes and towering creatures that hadn't really been seen in games before. Then the masterpiece and my favorite game, Uncharted 2 for the PlayStation 3, had incredibly great graphics and lighting, along with an amazing artistic direction. And Red Dead Redemption also released on the PlayStation 3, featuring one of the biggest interactable open worlds with jaw-dropping landscapes and story. Well, why exactly am I mentioning all of these? Because they were all built with strict hardware limitations, and that's a good thing. Developers knew the exact specs of each hardware, how much memory it had, how fast the CPU was, how fast the GPU processed graphics, and even the quirks of the storage system. And because everyone who played the game had this same machine, developers could squeeze out every last drop of performance, which made it easier to hit stable frame rates. For example, on earlier consoles, a lot of titles targeted 60 frames per second and weren't allowed to ship the game if it dropped below that at any point. Nowadays, though, game companies not only have to target consoles, but PCs, which have grown tremendously in popularity over the last 2 decades. And PC land, it's the Wild West, really. Not only does a game need to run on a laptop with integrated graphics, but also scale up to a high-end gaming rig with an RTX 5090. And even if a high-end PC has more raw power than a console, a lot of that power isn't always directed to the game. John Carmack, one of the most famous game developers of all time, and one of the creators of Doom, estimated that a gaming PC might only use about half of its available power towards a game, which isn't a lot for some of these huge games, just because the rest of it is eaten up by Windows, drivers, API overhead, and just the inefficiencies of trying to cater to so many different types of computers. It's also important to note that modern consoles also benefit from unified memory architectures, meaning that the GPU and the CPU share the same high-speed RAM pool. This not only simplifies data management, but it also lets the console stream data from its solid-state drive extremely fast with minimal CPU usage. Heck, studios like Naughty Dog use the PlayStation 3's specialized Synergistic Processing Unit, or SPU, to offload a lot of the tasks from the CPU efficiently to achieve their groundbreaking graphics, compared to most studios that didn't even touch it because of its complexity. Console SDKs, or software development packages, lets developers access specific low-level tools to profile and squeeze every last drop of performance. With PCs, you don't really know what you're gonna get, so you just have to try your best to keep the game running as good as possible and as steady as possible. However, on PCs, there are more graphic settings options, so players can sort of tweak the game to their liking to match their specs. And all of this is just assuming Windows. I'm not even mentioning Mac or Linux. For example, my friend and I recently developed a game called Desktop Cat Cafe made with Unity, and it runs on your desktop, and it was so difficult to get it to run on everyone's computers. It was a nightmare. During development, it would work flawlessly on his computer, but then it would just completely break on mine for some reason. And only after a couple months of debugging and Walter, my friend, continuously adjusting the Windows code, were we finally successful. And we were only able to launch on Windows for the time being because every different operating system requires custom code for the transparency to work. Even after launch, some of our players had issues we could just not replicate, making fixing bugs in a timely manner really difficult. And we're just a small 2-person team. Imagine like 100 people or 1,000 people trying to make everything work. That's horrible. Anyways, we fixed those bugs and our game is really cute and keeps you company while you work or play. So you should buy it to help support me and pay my rent, please. Sorry, I think that clap was a little loud. But this still doesn't paint the whole picture and leaves a lot of unanswered questions. Why does it seem like graphics are getting blurrier? Older games seem to look crisp, so why do all these new games look like you need glasses to really appreciate them? But it's okay, because I got some Or why are games launching with game-breaking bugs and performance issues leading to overwhelmingly negative reviews on Steam for loved franchises? And who the heck is at fault here? But before that, there's something you can do to make the game industry a much better place, and that's making your own game. It can be pretty overwhelming knowing where to start, but luckily GameMaker, the sponsor of this video, is one of the best game engines you can use to get started on your game development journey. Home to famous games like Undertale, Hotline Miami, Spelunky, and Hyper Light Drifter, the engine is perfectly suited for making both simple and complex 2D games. Not only is the engine fast and supports visual coding, but it's also completely free to export to any non-console platform, and a commercial license is a simple and one-time affordable fee, so you don't have to worry about calculating percentages or keeping track of how many people bought your game. I've been making my own game with GameMaker called Boombi, and I loved how easy it was to prototype in and get a game up and running in no time. With no previous experience in the engine, I was able to make an entire platformer in only 1 month, with their easy to understand language, GML. They have templates to help you get started, great documentation on their website, and even post really nice tutorials on their YouTube channel with tons of variety on game mechanics. So get started making your own game now, today, right now, with GameMaker, with the link down in the description. Now, let's talk about blurriness in video games, a common pain point for many newer titles. Just imagine you pay $70 or $80 now to download a highly anticipated AAA game that you've been waiting years to release, watch a super awesome starting cutscene, and then when you enter the game, it looks like someone rubbed Vaseline all over your screen. The edges look soft, distant objects shimmer or seem to dance around, and instead of the sharp visuals you expected, the entire game feels like it's being viewed through a pair of dirty glasses. Not me though. Mine are clean. So you try changing some in-game settings, like reducing the motion blur, and even check your monitor to see if it's running at the best hertz spec. But the problem isn't you, it's them. And it's got a name. Temporal anti-aliasing, or TAA. And you know it's bad when you have an entire subreddit dedicated to hating on it. To understand why it looks so smeared and blurry, first let's look at what anti-aliasing means, and then why studios keep on using this method if clearly most people hate it. Anti-aliasing is a technique used to reduce jagged edges, those little stair-step lines you see at the edge of the 3D models, especially in older games. It's basically trying to make the digital lines look smoother so it can look more like the real world. For example, here's a comparison between no anti-aliasing and SSAA, or super sampling anti-aliasing, which renders the game at a higher resolution and then scales it down so it appears smoother. Now, there are a bunch of different types of anti-aliasing. You've got fast approximate anti-aliasing, or FXAA, multi-sample anti-aliasing, or MSAA, subpixel morphological anti-aliasing, SMAA, and of course the infamous TAA. Earlier methods like MSAA actually sampled the scene multiple times per pixel to figure out where the edge is, and blur it just enough to make it look smooth. It was clean, crisp, and relatively easy to work with, but there was one big issue. It was kind of expensive, performance-wise. Then came fast approximate anti-aliasing, FXAA, which was faster, but also kind of lazy, because it pretty much just blurred everything. And that's when these softer images started creeping into our games. And finally, TAA enters the room, wearing a lab coat and promising a smarter solution. Temporal anti-aliasing doesn't just look at one frame, it looks at multiple, before and after, and tries to figure out what's moving, what's aliasing, and what's just noise. In theory, it is very cool. By blending together data over time, you get smoother edges, less flickering, and more stable images during motion. But in reality, it often leads to a soft, blurry piece of work. If the algorithm misjudges something, or if you're just moving the camera too quickly, TAA can leave behind ghost trails, smearing effects, or straight up blur important details. It's like your game is constantly being repainted with a wet brush. And here's the worst part. Some games force it on you with no way to turn it off. So now you're stuck with your $70 500GB game with a permanent smear mode. So if it has so many problems, why do people still use it? Well, it's cheap, performance-wise, it's flexible, and it hides a lot of visual noise. It helps with shimmering and complex scenes, especially with things like foliage or fine geometry. And when combined with modern upscaling techniques like DLSS, deep learning super sampling, or FSR, Fidelity FX super resolution, it becomes a key part of stabilizing the image. And when done right, you you can get some really nice results with it. But when it's not done right, that's when it looks like a big mushy mess. It's a big reason why a game from 10 years ago might feel sharper and more solid than something released last month, even if the new game is technically doing way more under the hood. Even worse, they often stack it with film grain, motion blur, depth of field, chromatic aberration, and pretty much every post-processing effect they stuff into it. Older games, especially from the early PlayStation and PC eras, didn't really rely on much heavy post-processing and ran at a native resolution with no fancy upscaling methods, and often had no anti-aliasing at all. Sounds depressing, right? Well, here's the part that a lot of people get wrong. Graphics have definitely been getting better. Under the hood, games today are doing way more than ever before. There's real-time global illumination, volumetric fog, physically based rendering, dynamic weather systems, complex shaders, micro details, and reflections that actually reflect the world around you. Just look at games like Cyberpunk 2077, or Metro Exodus Enhanced, or even Control. With ray tracing and DLSS turned on, these games end up looking like an impressive tech demo. As an example, let's just compare the Resident Evil 4 remake to the original. It has the same characters, same story, but now it has atmospheric lighting, fluid animation, and tiny environment details that just weren't possible back then, which makes it feel like an entirely new game. Now, the difference might not always be visible in a paused screenshot, but it's in the combination of the motion, the ambience, the light bouncing, and the shadows reacting in real time. And all of these things take a lot of processing power, so yeah, compromises need to happen so it can continue running smoothly. Take lighting, for example. Back then, you couldn't just throw 20 lights into a scene and expect it to work. Every light added to the level had a cost, so most games used a trick called light baking, and a lot of them still do actually. So instead of calculating how light behaves in real time, which usually involves dozens or even hundreds of rays bouncing around the environment, the lighting is pre-calculated, like a screenshot burned into the environment. Shadows, reflections, bounce lighting, all of it was baked into the textures and applied directly to the scene. It looked great, but under one condition: nothing could move. You couldn't turn off a light, break a window, or change the time of day, because all of it was pre-rendered and locked in. However, studios would get around this by baking the lights for multiple possibilities and just switching between them. Nowadays, though, lighting runs at real time. You can walk into a room, shoot out a light bulb, and the shadows will react instantly. Light bounces off the walls, reflects off puddles, and floods through the fog as you play. A great example of both performant and next-gen lighting is Half-Life Alyx, which showed off incredible graphics on VR with meticulous attention to detail, high-quality textures, and really good lighting. But there was a catch. They used Valve's huge data farm to bake all of the lighting in the game to account for multiple actions the player might make, which not only made it look good, but made it run extremely well. But most normal studios or developers don't have access to these huge options. But people tend to forget about all of these advancements. Instead, they compare it to what they remember: the crisp, clean image from 2008 running at 60 FPS on a flat screen TV. And now they compare it to a blurry launch build of a modern open world game loaded with a boatload of dynamic systems and bugs. So they might say that games used to look better, but in reality, they just looked cleaner. And a big part of that comes down to art direction. Technical fidelity, all the polygons, all the pixels, all the fancy lighting means nothing if the presentation is weak. Games like Windbreaker, Journey, or even Team Fortress 2 still hold up today. Not because of the cutting edge graphics, but because they committed to a strong visual identity with colors that pop and shapes that read clearly. Everything is built to look good as a cohesive whole. Meanwhile, some modern games chase realism so hard that they end up looking kind of gray. Blown out bloom, washed out colors, or so many effects that the scene just becomes super hard to read. But that's not really a tech problem, that's more of an art problem. So yes, graphics have improved. A lot, actually, but the way we perceive those graphics is skewed or biased. Because what we see as worse graphics is often just overused post-processing, muddy image reconstruction, and a really underwhelming visual design. So they're not uglier, they're just harder to see. And I have something just for that. But what about performance? If games look better and do way more than ever before, why do they run like poop? You'd think with all the next-gen consoles and all these fancy GPUs, the new games would be faster.
Not exactly.
Modern games now have to deal with way more systems and mechanics all at once. Real-time lighting, huge open worlds, hundreds of AI agents, physics-based everything, volumetrics, particle systems, cloth simulations, all running at the same frickin' time. And the older games, they didn't really have to deal with all that. They were smaller, more focused, and easier to optimize. But today's games don't only have to be cinematic, but they have to be huge, and everything has to interact with everything, because if the puddle doesn't interact with the player, then you'll get like a million negative reviews. And all that takes a lot of power. And here's the thing, hardware improvements have kind of plateaued. We're no longer getting those massive leaps in raw power every couple of years like we used to. Moore's law, the idea that processing power doubles roughly every 18 to 24 months, is slowing down dramatically. Meanwhile, the demands on games are skyrocketing. We want 4K, 60 FPS, ray tracing, realistic animation, big worlds, fast loading times, all at once. And the studios are under a lot of pressure to deliver all of that across 5 platforms at the same time. So even if you have a beefy rig, most games are built for a wide amount of platforms, and that means that performance often gets scaled down to keep everything consistent. Add in crunch time, giant teams spread across the whole world, and the expectation to patch everything later during release, it's no surprise that more games are launching with game-breaking bugs and stutters and crashes. Because back in the day, patches weren't really a thing. If your game shipped with a bug on the cartridge or a disc, it was done. It lived there forever. So developers really had no choice but to test everything before release. Optimization wasn't really optional. It was a necessity in every step of the game development process. Games had to run well on day 1 because there was no day 2. Or you have to risk producing a ton of more physical CDs or cartridges, which would spell disaster for a studio. Today though, there's a nice safety net. Day 1 patches, post-launch updates, performance hotfixes, that's the new norm. And that's kind of led to a shift in priorities, so a lot of games often ship knowing that they'll have to fix stuff after release. It's really hard making a game, okay? And it's important to not forget that developers often have to build entire systems just to keep everything in sync between the different platforms. From asset streaming to resolution scaling to control schemes, and instead of making one great version of a game, devs now have to make 5 to 7 slightly worse versions of the game that work everywhere. This just means more testing, more bugs, and bugs that might not even appear in the platform where they make the most money. And then the most important thing is money. These games cost hundreds of millions of dollars to make. They have investors, publishers, and marketing campaigns lined up months in advance. There are bonuses tied to fiscal quarters, pre-orders, and major sales windows like in the holidays. So when a game gets delayed, it's not just about polishing it, it's about losing a lot of money in the process. They can lose millions of dollars, which could risk the entire studio, future projects, and investor confidence. So even if a game is not ready, sometimes they launch it anyways, because shipping something broken is safer than delaying it and earning nothing. And then what happens? You get that nice day 1 patch, maybe a performance update 2 weeks later, and if you're lucky, maybe a stable game in 1 to 2 months. But by then, the damage is done and the Steam reviews are brutal. But we're still missing an important point about this argument, and a lot of YouTube videos have been created in the last couple of months regarding this. You may already know what I'm talking about. It's the new shiny kid on the block that's supposedly the #1 cause of all these issues, according to gamers. When the announcement for Unreal Engine 5 was first made, everyone, including myself, was understandably very hyped. Epic showed off an incredible tech demo along with Nanite and Lumen that they promised would revolutionize gaming, and in many ways it does. Nanite lets artists throw in ultra-detailed models without really any worry, except well, the download size of the game. And in cases where worlds are huge, it's a big time saver for studios without having to worry about traditional LODs, which is like essentially having the same model multiple times, all made in different resolutions, so you can easily switch between them in game depending on the distance of the player. And of course, there's some tools that automate this. Lumen, on the other hand, gives you dynamic real-time lighting without baking or light maps. It's extremely powerful and flexible, which allows for tons of lights to be in the scene, all reacting dynamically at once. But here's the thing, Unreal Engine 5 is still relatively new. It's a big big engine with a lot of complexity, and it's ever evolving, making improvements in every version. And most studios are still learning how to use it effectively, especially on consoles and lower-end PCs. And yet publishers are already greenlighting full-scale AAA games on it, when really all they want is that next-gen label and the hype around it. So we're seeing games launch in Unreal Engine 5 that are clearly not ready. They stutter, they crash, and they run at low internal resolutions and rely on aggressive upscaling. And then when gamers play it, they go, oh man, another Unreal Engine 5 game. But it's not the engine's fault. Not entirely. It's a tool. And like any tool, it depends on how it's used. When implemented right, Unreal Engine 5 can produce some of the most visually impressive scenes we've ever seen in games. But when rushed or pushed too far, it can lead to blurry visuals, huge system requirements, and a lot of complaints. And let's not forget that you can still use all these old techniques in the engine. It's not like they just disappeared and everyone just decides to use TAA because they feel like it. So no, Unreal Engine 5 does not deserve the hate it's getting. Sorry. When in reality, it's just being blamed because expectations are really high and studios don't really have the time nor the ability to push out these AAA games and meet these expectations. And now that it's easier than ever to make games with it, more people are using it who may not have as much experience with the engine or with game development. So a lot of these games that are released on Unreal Engine are seen by gamers as slops. And so Unreal just continues to earn a worse name because the developers are just not utilizing it to its maximum capability, which I think is fine in some cases. Not every game developer needs to make the next most optimized Cyberpunk 77, whatever it's called. But good news, this stuff will get better with time. Hardware will start to catch up, and tools like Nanite, Lumen, DLSS, and FSR will just get better. We'll start seeing games that really deliver on that next-gen promise, without sacrificing performance or clarity. But right now, we're just in that middle awkward phase. And during that phase, gamers complain. And you know what? Sometimes it's totally fair. If you paid $70 for a game, you have a right to be annoyed if it just doesn't work when you purchase it, or if it's just smeared in motion blur or TAA. But on the other side, a lot of players don't really understand what's going on under the hood. They just know that something feels off. So they'll blame the developers, the engine, the console. They'll post side-by-side screenshots comparing a 2023 release to a 10-year-old game and say, look, the old one is better. The graphics state sucks. But what they're really seeing is the result of a lot of complexity, performance trade-offs, and rushed pipelines, wrapped in a layer of visual effects and TAA blur. So are games evolving backwards? No. It's just that expectations are way higher, systems are more complicated, and the margin for error is very small. Along with the deadlines and the patches, what used to feel simple and solid now feels bloated and broken. Now, it's easy to point fingers, but the truth is, it's not just one issue, it's everything all at once. Making games is extremely hard. It's one of the hardest things I've ever done. But once you've made a game, I bet most gamers would change their perspective and start to be a little nicer towards developers. I lost some hair making my past game. So if you want to be one of those elite people, you should totally learn how to make a game and sell it with my video here, and also purchase my game because it helps me a lot and I would really appreciate it. Gracias.